Hello everyone. Today we are going to discuss the topic of differentiability. And what is differentiability really? We say that a function is differentiable at a given point when the derivative of the function at that point exists. So does that mean that the derivative doesn't always exist? Yes, of course. That's exactly what it means. We do not always have a derivative for the function at every given point. For this topic, I'm assuming that you have the following prerequisite knowledge. I'm assuming that you know when a limit does exist and that you know how to evaluate a limit. I'm also assuming that you know when a function is said to be continuous, although we will review this very quickly as we go. And most importantly, I'm assuming that you know the formal definition of the derivative. But we will review this because it's very relevant to the topic at hand. Let's start by reviewing the formal definition of a derivative. What is that? Now, a derivative is defined as follows. F prime at a, which is the derivative of the function that we call f, at the point where x equals a. This is defined as the limit as h approaches 0 of this thing, which is what we call the difference quotient. It is f at a plus h minus f at a all over h. This is the formal definition of the derivative, and you should be familiar with it. Now, as you can see, the derivative is a limit. The derivative is not just a regular function, which means because a limit doesn't always exist, this also means that the derivative does not necessarily exist. So, graphically speaking, what does that mean? If you remember from the definition of the derivative, this means that we take a point on the graph and we draw a secant line between the point of interest and that point, and then we bring the 2 points closer and closer to each other, and this way the secant line gradually approaches a tangent line. So let us actually see how this looks like graphically. As you can see here, I have a function and there is a point on this function. I try to fix this point for the rest of the examples. I try to fix this point at where x equals 1, and I am going to choose another point here, point R, to the right of point A, as you can see, and we will connect the point R with point A with a line, as you can see here. This line is called the secant line. But as we bring this R closer and closer and closer and closer to point A, do you see what's happening now? This line is approaching a tangent to the graph, which is a line that just touches the graph at that point. Now, if we zoom in here, let's zoom in again. Do you see what's happening? It's just touching the graph. All right? Now, the slope of this line, the slope of the tangent, is actually what we call the derivative, which is also the instantaneous rate of change. Now notice what happens when we have a point to the left of A, not to the right, which is this point right here, point L. Now I can also connect a line from point A to point L, and that also would be a secant line. But what happens when I bring point L closer and closer and closer and closer to point A? Also, this secant line approaches a tangent. But look, I'm going to zoom in here. Look at what is happening. the tangent is the same. The line that we are approaching by bringing point R from the right and bringing point L from the left closer and closer and closer to point A is actually the same. They're approaching one and the same line. And that line is the tangent to the graph at A, and the slope of the tangent is the derivative of the function and is the instantaneous rate of change of the function at this point A in this case. So graphically speaking, that's how we get the derivative. And in this case, the derivative does exist. But the derivative doesn't really always exist. Why? Let's see why. If you look here, this limit, the definition of the limit, has this in it, which is the value of the function at x equals a. So if we do not have a function at this point, if the function is undefined at this point, we cannot possibly evaluate this limit because we don't know what to put there. So number one reason for the derivative not to exist is if the function at that point is undefined. We don't know what the function is. It doesn't exist. So for example, look at this graph. This graph right here, you can see the definition of the function to the left. But in this graph, there is a hole in the graph. Exactly where x equals 1, the function is undefined. I have no clue what the function is. The point doesn't exist. So even if I have a point on the right and the point on the left, this point R over here and this point L over here, and I do want to connect point R to a point on the function where x equals 1, I don't know what to do because this point doesn't exist. So it's impossible. And the same for point L. I don't know where to connect the line to. Notice that I'm not connecting point L to point R. No. I want to connect point R to some point on the graph of the function where x equals 1. But this point is missing. And that's why it's impossible in this case. So now you know one reason, or the first reason, why the derivative of a function might not exist. All right. So what is another possibility for the derivative not to exist? Remember that this derivative right here, this is also the slope of the tangent at x equals a. If you draw a tangent to the line at that point, this derivative is the slope of the tangent. Okay, so let's ask ourselves the following question. Does every line, because the tangent is a line, does every line has a defined slope? The answer is no. And I'll give you a moment to think of when would a line not have a defined slope. Any ideas? When you have a vertical line. A vertical line does not have a defined slope. And hopefully you remember that from like grade 9 or 10 or something like this. So look at this function right here. This function here is essentially a transformed cubic root function. Don't worry about what the function is, but look at what happens at point A right here. It's still at 1 and 0 in this case, and this point is defined because the cubic root in this case is 0. So we have a defined point. But the tangent in this case is a vertical line. So let's see if we have the point R right here to the right of A, and if we connect R to A like this to get a secant line, and then we bring R closer and closer and closer and closer to A. Look at what's happening to this line. Look, 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 look. This line is approaching. Now I overshot here, overshot. Right. Look, I'm trying to bring it closer and closer. And what's happening here? What's happening? It's approaching a vertical line. Okay. That's what's happening from the right side. What's happening from the left side? That's a point L over here to the left of A, and I'm going to connect L to A to get a secant line, and then I'm going to bring L closer and closer and closer to A, and let's zoom in and bring it closer and closer, even closer and closer and closer and closer and closer. And what's happening here? What's happening? It's also approaching a vertical line. So as a matter of fact, this is the tangent. You see the dotted red line there? This is the tangent to the graph at that point. The tangent is a vertical line. I'm going to remove the two other lines so you can see the tangent. Do you see? Now this is the tangent. It is a vertical line, and the slope of a vertical line is undefined. And this is why that's another case where the derivative is undefined. It doesn't exist. So far we learned about two cases where we don't have a derivative. The first case is when the function itself is undefined. I don't have a value for the function. The second case is when the tangent to the graph of the function is vertical. All right? The third case is slightly more complicated. It's not very complicated, but it is more complicated than the others. So, hopefully you remember when a function is discontinuous. So what are the types of continuity that you remember? Number one is we have something called removable or point discontinuity. And that's what we typically call a hole in the graph. So a hole in the graph does not necessarily mean that the function is undefined at that point. And I'll give you an example for that right away. This is one of the functions that we talked about earlier that had a hole there. But if you look here to the left, this function is defined piecewise. So where we have a hole, we also have a definition for the function. Where x is equal to 1, the function is defined to be of value 1. So we go on the graph of the function all the way from the left, all the way from the right, approaching the hole, but exactly at the hole, the function jumps up to that point A. So the problem here is not that the function is undefined. No, the function is defined, but it is discontinuous. So what's the effect of that? Again, let's do the same thing. We have a point R to the right of where x equals 1, and we will connect this point with the point on the function, which is in this case, this is A, this is point A, it's not the whole. Where x is 1, the function is up there at 1, at point A. So we connect that, we get a secant line. And then we bring this point closer and closer and closer and closer. And what is happening as you observe that? Let me get closer here and bring it closer and closer and closer. And what is this line approaching? What is it approaching? It's approaching a vertical line. So we have the same problem again. The slope of a vertical line is undefined. But what if we come from the left side? So this is the point on the left, right here. And we're going to connect this point with the point on the graph of the function. And we will do the same thing. We will bring this point closer and closer and closer and closer. And as we bring it closer and closer and closer, what is happening to this secant line? It's approaching what? Approaching a vertical line. And if you don't believe me, let's just zoom in a bit. Zoom in here and bring this point closer and closer again, and bring this point closer and closer again. And what is happening as we do that? The line is becoming more and more vertical. So this is why when we have a situation like this, when we have point discontinuity, even if the function is defined, we still do not have a derivative for the function. All right? Now, what else? What other scenarios? We said that one type of discontinuity is when we have removable discontinuity. Another type of discontinuity is when we have asymptotic or infinite discontinuity. And this is where we have a vertical asymptote for the function, where the function has a vertical asymptote. One may think that where the function has a vertical asymptote, it is necessarily undefined there. Well, no, not really. We can make it defined there if we have a piecewise defined function, like the following. This is a function right here. The definition of the function is on the left, as you can see. And the function is actually defined at x equals 1, as you can see. But at that point, it has a vertical asymptote. As you get closer and closer to 1 from the right side, the function shoots sharply all the way to positive infinity. This doesn't happen from the left side, but it does happen from the right side. So we still have a vertical asymptote there. So let's do what we did before. The function is defined at x equals 1. It is the point A over there. We have a point on the function to the right of A, which is point R. We connect this point to point A with a line. That is supposed to be the secant line. But what happens as we bring R closer and closer and closer and closer? Ooh, look at that. Look at that. What's happening here? The line is approaching a vertical line. If we try to go up here and bring it a bit closer, you see what happens now? It's almost vertical. You cannot tell that it has any inclination whatsoever. We may be able to tell if we zoom in right here. Yeah, there is just a slight difference up here. So it's almost vertical. Now, in this case, if we have a point to the left of A and we connect that point to A right like that, and we bring this point closer and closer and closer to the A on the graph, we are actually not approaching a vertical line. So from the left side, we're actually approaching a regular tangent. It's not a vertical line. But what happens from the right side? From the right side, we're approaching a vertical line. So now they are not even the same line. They are not even, it's not like this one is vertical and this one is also vertical. No, this one is vertical and this one has a finite value. And if you remember from the definition of the existence of a limit exists when the left-sided limit is the same as the right-sided limit. They are the same value, but here the left-sided limit will give you a finite value because we have a regular line and a slanted line with a finite slope from the left side. But from the right side, what's the case? We are approaching a vertical line which does not have any defined slope. So if we have an asymptotic discontinuity, the function is still non-differentiable there. The derivative does not exist at this point, even if the function is defined at that value. All right. Now, are we done with the types of discontinuity? No, there is a third type. Hopefully, you still remember about this third type. The third type of discontinuity is the jump discontinuity. And that is where the function suddenly goes from one y value all of a sudden to another y value, jumping from one value to another, hence the name, jump discontinuity. So let's take a look at this and see. This is an example of jump discontinuity right there. The definition of the function is to the left, as you can see. The point that belongs to the function is point A over there. In this case, I actually forgot to put a hole where we have 1 and 0. So this here is a hole. So this point h down there does not belong to the graph of the function. It's a that belongs to the graph. So again, we put a point to the right of a and connect that point to a, and we bring it closer and closer and closer and closer from the right side, and as you can see, we are actually approaching a slanted line. We kind of have a tangent when we are coming from the right side of A. But what happens when we come from the left side of A? This is point L down here on the left side. We will connect it to point A with this line, and then we'll bring it closer and closer and closer and closer. Looks fine so far, but bring it closer and closer again and again and again. And what is happening? What is happening here? Look, we're approaching what? Bring it closer again. We're approaching what? We're approaching a vertical line. We're approaching a vertical line, and that is pretty much the same problem that we had before. From one side, we have a slanted line with a finite slope. From the other side, we're approaching a vertical line with an undefined slope. Therefore, the limit from this side is not the same as the limit from that side, and the function does not exist. Not the function, the derivative. The derivative does not exist because the limit does not exist. All right? So, in those three cases, which are the cases of discontinuity, in all of them, the function does not have a derivative where it is discontinuous. So, let's recap so far. What are the what are the cases are where we do not find a derivative. We don't have a derivative for the function. We said number one was where the function is undefined for any reason, right? But someone may have a may catch something here. Someone may tell me that, well, if the function is undefined, it is discontinuous. If you remember the necessary and sufficient conditions for continuity, the function has to be defined at the point where it's said to be continuous. So if the function is undefined, it is also discontinuous, right? So we can add that to the three cases of discontinuity right there. So whether we have a whole or a vertical asymptote, in which case the function is undefined, right? Uh, or whether it is defined as we showed in our examples. The fact that we have a whole doesn't necessarily mean that the function is undefined. It can be defined. Same thing for the vertical asymptote. The function can be defined if it's defined piecewise. But if it's discontinuous, now we have a bigger category. If the function is discontinuous at any point, it has to be non-differentiable at this point, which means the derivative at this point does not exist. The other thing that we talked about is where the tangent to the graph of the function is a vertical line, because the slope of a vertical line is undefined. But notice when we were discussing what happens in the case of discontinuity, we discussed, or we found a very interesting thing, that we may have a different line, different we may be approaching a different tangent from the left than from the right. And that's why the derivative in this case wouldn't exist, because the limit wouldn't exist. And that's another scenario for when the function doesn't have a derivative. Now look at this. This is our very friendly, very familiar absolute value function. The absolute value function is quite simple actually. The definition is over here to the left, and point A here is a point on the function, so the function is continuous. We don't have a problem with that. But now we have this point R on the right. If we connect R with A, what do we get? We get this line, and it doesn't matter what you do with R because the function is linear to the right of A. Doesn't matter how close you bring it, you always get this green line. So the tangent coming from the right side is always this green line. Is it a slanted line or a vertical line? It's a slanted line. Does it have a finite slope? Yes, it has a finite slope. So, okay, we have a slope from the right. What about the left? This point is on the left right here. Let's connect that with point A. See what happens here? We have this orange line coming from the left, and it doesn't matter what we do, it doesn't matter how close we approach from the left. Because it's linear to the left, we always get this orange line. So approaching from the left side, we're approaching this orange line. Approaching from the right side, we're approaching the green line. But clearly, the two lines do not have the same slope, which means the limit coming from the right is not the same as the limit coming from the left, which means the limit does not exist. But as we said earlier, the derivative is a limit. The limit doesn't exist because approaching from the left not the same as approaching from the right. Therefore, the derivative at this point A over there, well, I hid the lines, yes. The derivative at this point A does not exist because of that, right? When we have a situation like this where we get a sudden change in the curvature, it doesn't have to be linear, by the way, as we will maybe see later. Doesn't have to be linear like this, but we have a sudden change in the curvature of the graph. This is what we call a corner. So wherever we have a corner in a graph with a sudden change in curvature, at that point the function does not have a derivative and the function is said to be non-differentiable. So what are so far what are the cases where the function or a function does not have a derivative, where it is non-differentiable? It's where the function is discontinuous, where the tangent to the graph of the function is a vertical line, and where we have a sudden change in the curvature of the function, which is typically called a corner. Some of you may hear in your school that we also don't have a derivative where we have a cusp. Well, a cusp is more or less one of the things that we discussed before. A cusp is where the tangent is vertical, but coming from the right side, it's one slope, as in positive or negative slope. Coming from the left side, it's the other. So it's positive from this side, it's negative from that side, but eventually the tangent is vertical at that point. It doesn't really matter. It falls under the uh, topics that we discussed before, or the items that we discussed before, which is a vertical tangent essentially. So again, let's repeat. When is a function non-differentiable, as in doesn't have a derivative? Where the function is discontinuous, where the tangent to the graph is vertical, and where there is a sudden change in curvature, in the curvature of the function, which is what we typically call a corner. So to recap, we will do a little practice here. Let me just prepare my screen. There you go. So we have this function. Obviously it's piecewise defined function. I kind of hid the definitions, and I want you to think with me at those points. Do we have a derivative, as in the function is differentiable, or we do not have a derivative, as in the function is non-differentiable? Starting with point A, I'll give you a couple of seconds to think. Point A, it seems that coming from the right side, coming from the left side, we're approaching the same curvature. We don't have any sudden change in the curvature of the function. The tangent doesn't seem to be a vertical line. The function is continuous. So yes, at point A, the function is differentiable. We do have a derivative. What about point B? Think with me. Point B, the tangent there is what? Looks like it's a vertical tangent, right? Yes. So the function is continuous and is defined, but The tangent at that point is a vertical tangent. So what? The function is non-differentiable. We do not have a derivative at that point, although it's continuous. How about point C? Couple of seconds to think. Well, point C is a jump discontinuity. You see, the y value goes from 1 to whatever it is down there. Suddenly, it drops suddenly. And we said that wherever a function is discontinuous, it is non-differentiable. So we do not have a derivative at point C. How about D? Okay. Is it continuous? Yes. Is the tangent vertical? No. Do we have a sudden change in curvature? Doesn't look like it. So, because of that, we do have a derivative at D, and the function is differentiable. How about E? Oh, doesn't look like this is very difficult. At E, we have a vertical asymptote. We have asymptotic discontinuity, and as we said, wherever a function is discontinuous, it does not have a derivative, so it is not differentiable at E. How about F? We don't have asymptotes there, and the function seems to be continuous. We're not jumping, we don't have holes, but we do have what? We do have a sudden change in curvature. So the function is going up like this, and all of a sudden turns and goes like that. So this sudden change in curvature means that the secant line approaching from the right is not the same as the secant line approaching from the left. So the left-sided and right-sided limits are not the same. The function is non-differentiable. The derivative does not exist at point F because of that. How about point G? That one doesn't seem to be difficult, is it? Is it not? It's not difficult. At point G, the function is continuous. There is no sudden change in the curvature of the function, and the tangent there is not vertical, doesn't seem to be vertical. So the function is differentiable there, and the derivative does exist there. I hope that was helpful. Wishing you all the best. See you soon.